And we are back, and today we are going to get into a very related topic to permutations, and that is combinations, which we can see. I'm going to erase combinations. Now, combinations and permutations, as you can see here, the formulas are fairly distinct, but we see one key difference. In our denominator, we see this additional factorial r. So we can already assume that the number of combinations will be less than the number of permutations in general and just really by definition. The key difference between a permutation and combination is in permutation, the order matters. So we are looking at the number of ways that we can basically choose a set of n distinct objects from a number of r objects, and the order and the particular arrangement is important. It matters. In combinations, however, the order does not matter. And let's go ahead and let's do a couple of examples and let's kind of put this to study. So first, let's say I have a class of 23 students. How many ways can we choose teams of 3? So as we've seen before, n is going to be, the number of objects is going to be 23, r is going to be 3, and we can kind of run through essentially the math and the operations here. Interestingly, if you increase essentially the team size to 8, we see an increase in the number of combinations. But let's bring it back a little bit to our previous example. So let's look at combinations where we had n equals 3 and r equals 2, as we can kind of see here. So previously for the permutations, and let's go ahead and let's bring up, let's keep going with r in order to kind of, again, practice r and also get used to some of these values. Because we said that we had n options A, B, C. So let's set n to 3. And actually, let's see, make sure we have that. And let's set r to 2. So let's set n to 3, control enter, let's set r to 2. And we can do our factorial. So we had factorial of n divided by factorial, factorial of n minus r. And let's see our value here. Control enter. We had 6, which is great. So now let's copy that same expression, but let's do now the combinations. So in the combination, let's copy here. We should have an additional, let's pull up our notes here. It should be multiplied by that factorial r. So factorial n, let's do factorial of r. And let's enter, let's do a multiply. And let's make sure that we have put these all underneath. And we see we have now only 3 combinations. So this is a very, very, very important, and it's actually what we expected just from our definition. But how do we get 3? That's a good question. I'm complimenting myself. So if I don't care about the sequence of arrangements, how many ways can I arrange, pick 2 from these 3 letters? Well, I can have A and B, right? I can have A and C, and I can have B and C. So these all check and they correlate, right? A and B here, A and C here, and then we have B and C here. Well, what about these others? Right here, and right here. Well, B and A, again, we don't care, again, in combinations, we don't care about the sequence, the order, effectively. So A and B is equivalent to B and A. C and A is equivalent to A and C and B are equivalent to B and C. So that's the key distinction. So the number of combinations implies effectively that I don't care about the order in which they're arranged. But the permutations, the number of distinct ways, if there is a reason why I need like a distinct set a distinct order, that is when we'll use that expression. So whenever you're doing a lot of these kind of permutations, probability, and statistics problem, it's important to read the problem carefully. And oftentimes the problem is posed in a way that's not necessarily clear. And I may do that unintentionally, obviously, at times. So when that happens, I would definitely suggest to suggest to try to get some clarity on that question. And next time we'll go ahead and get started in probability. See you next time. Bye.